Now let's start with group 16. Group
Yes.
16s are called chalcogens.
Chalcogens.
Chalcogens
Okay.
implies they are ore containing elements.
Okay.
Most of the metal ores are either oxides and sulfides.
ठीक है.
Okay, that's why they are called chalcogens. By nature, oxygen and sulfur are non-metals. Selenium, tellurium are metalloids, and polonium is
Right.
metal, and it's a radioactive metal.
Right.
Oxygen usually exists as a dimer at room temperature. It possesses a
Right.
pi-pi bond, which is very strong, and that's the reason why it does not go anything beyond a dimer formation. Okay.
Okay.
Usually 2p pi bonding is greater than 2p pi d pi and 2p pi 3p pi and 3p pi 3p
And
pi.
3p
So
by
that's
3p
why
by.
chances of making an S double bond S would be very rare, because then you have to make a p pi and p pi
P
over
by.
here.
Hmm.
Hence, sulfur, selenium, tellurium, they usually exist in allotropic forms where they will have single bonds more often observed. Polonium is
Right.
simply a solid with more of metallic bonds. Okay.
Hmm.
Sulfur exists as S8, which is more of crown shape. Same is the case with selenium. Tellurium will have a chair shape here, like this. This will be taking a chair form with 6 tellurium
Okay.
form. Now,
And
size
polonium.
wise, there is a regular increase in the atomic size down the group. Ionization, regular decrease in the ionization. Electron affinity is an exception. Oxygen, which is expected to have very high electron affinity, will have the
Right.
least in this case. Okay.
Okay.
Although all the electron gain enthalpies are negative only. Okay. But the second electron gain enthalpy is always positive. Got
Okay.
it? Second gain enthalpy is
Yes,
always
sir.
positive. And the first negative value of oxygen compared to others is less because of
Hmm.
electron repulsion happening. Okay.
Right.
Next, electronegativity wise, it's a regular trend down the group. In fact, oxygen is the second best electronegative element after fluorine. Melting
Hmm.
point wise, down the group, it is supposed to increase, and that's the way it is, except for polonium, which will have an inert pair effect and a weak metallic bonding. Thus, tellurium will have a more or better boiling point and melting point.
Right.
The general oxidation state of these elements, if you compare, oxygen has anywhere from -2 to +2. Sulfur will have -2 to +6. Selenium will have the same. Tellurium will have the same. In
Hmm.
fact, sulfur and selenium also give +1 oxidation state, which tellurium does not. I mean, tellurium is not able to see that. Okay.
Right.
You see, oxygen has all these different oxidation states: +1, +2, -1/2, -1, -2, and so on. And you have specific
Right.
names assigned to it. If it is -1, it is peroxide. -1/2, it is superoxide. +1, it is simply oxy, and it is
Oxy.
monooxy. This is difluoro.
Dioxy.
Okay. And sulfur with +1 oxidation state observed with halogens as S2Cl2, S2Br2, and so on.
Okay.
Sulfur can show +4, it can show -2 with hydrogen.
Right.
Polonium, you are expecting it to show +6, but due to inert pair effect, it does not show +6 either.
Okay.
Now, stability of -2 decreases down the group, because down the group metallic nature is increasing. So ability
Right.
to accept electrons, their electronegativity also less. So they will not have the ability to accept electrons. They will have ability to more donate electrons.
You need electrons. Hmm.
Next, stability of +6 oxidation state decreases and +4 oxidation state increases. Okay, it increases down the group.
Right.
And next you see covalency, maximum number of bonds an element can form, that is called the covalency.
Right.
Oxygen can make a covalency of 4, polonium can make 4, sulfur, selenium, tellurium can make 6. That means 6 bonds are possible at a time for these groups, for
Wait.
these elements.
Oxygen can make 4 bonds.
Yes, beta. This is the example you can see. Okay, known as basic beryllium nitrate. In this, oxygen makes 2 simple sigma bonds and two dative bonds.
Acha, हाँ.
Other two
It has
benzene.
two lone pairs also.
It has two lone pairs. This is called basic beryllium nitrate. This is one of the compounds where oxygen has actually four bonds. Its covalency
Right.
is four. Okay.
Yes, sir.
Next, what are the types of hydrides you will notice? See, H2O exists in liquid state, while H2S2 tellurium is gaseous and H2PO is radioactive gas. This is also gaseous form, but it is radioactive.
Okay.
What are the general trends we need to know from hydrides? First, bond energy. Down the group, bond energy decreases. Obviously, O and H will
Right.
have a stronger bonding, and
Right.
acidic strength increases down the group because it is easy to
Okay.
break the molecule and give away H plus. So
Hmm.
H2TE will have more acidic strength. Thermal
Right.
stability decreases down the group because thermal stability is directly related to bond dissociation energy. Boiling
Right.
point, you notice that we have to kind of give weightage to molar mass as well as hydrogen bonding. Hydrogen bonding
Right.
definitely is a much bigger factor. So water exceptionally have very high boiling point. Then after H2O, then comes the rest of the compounds based on molecular weight. So tellurium will have more molecular weight than selenium, then sulfur. So this will be the order of boiling point. But thereafter, melting point will have a very similar order. Okay. Bond angle, you see water has around 104 degrees, but rest all of
Right.
them will have decreasing angle because of the Draco's rule. Got it?
Huh.
As per Draco's rule,
Hybridization.
yeah, they are unhybridized. All these three are
Unhybridized.
unhybridized. They'll have
Right.
more or less angle as 90
90
degrees.
degrees almost.
Hmm. Reducing nature wise, down the group, reducing nature increases. So all of them, it is easier to give away hydrogens, so that increases their reducing property. Okay. Now
Yes,
this
sir.
is about hydrides. Now let's talk about oxides. These elements will form two types of oxides, EO2 and EO3. Okay.
Yes, sir.
EO2 includes SO2, SeO2, TO2, and POO2. These two are highly covalent oxides, and these two remain ionic oxides. And every oxide in this case is acidic except for tellurium and polonium. Okay. So where TeO2 and POO2 are amphoteric nature. These two are amphoteric in nature. SO2 on hydrolysis will give you H2SO3 acid. Selenium will give
Right.
you H2S2O3 acid. Okay.
Right.
Now, when it comes to SO2, if you recall, it would have p pi d pi bond, and the other bond will be p pi p pi bond. At least one will be p pi bond, the other one will be p pi d pi bond. Okay.
Right.
While selenium, because its double bond formation is weaker, it cannot keep making double bond all the time. It would exist in a
Hmm.
polymeric form and converts into a solid form. Okay, clear beta? And you know that
Yes, sir.
this p pi d pi bond is, I mean, this one is stronger, this one is weaker.
Weaker.
This p pi
Hmm.
bond is weaker, so that's why here you will have p pi d pi bond, p pi d pi bond. But on the other hand, it will start expanding, extending into a polymeric form.
Come on, sir. Hmm.
Selenium dioxide reactions, if you compare, in organic reactions, we learned if you have an aldehyde or a ketone at alpha position, oxidation will take place.
Right.
And if it is an allylic alkene, then we will have allylic alcohol formation with SCO2. SCO2 followed by
Right.
hydrolysis, and that's what will happen. We have came across these reactions in organic.
Hmm.
Down the group, acidic strength decreases for O2. Reducing character also decreases down the group here. Okay. Oxidizing character increases down the group. Okay. Although
Right.
it appears like as if tellurium plus 4 is more stable because down the group the plus 4
Hmm.
stability increases. But
Yeah.
TeO2, as soon as you heat it or just bring it over the more than room temperature, it will start reducing easily. Tellurium will
Okay.
get reduced and oxygen will get oxidized.
Okay.
Okay. So therefore, it can act like a better oxidizing agent here. Got it?
Hmm. Yes, sir.
And next, if you compare SO2, SCO3, SO3, SCO3, and TO3, all
Hmm.
these three are good oxidizing agents.
Right.
Of course, they are at the highest oxidation state, so they cannot be reducing agents.
Reduced any further.
Okay, yeah. And between these three, if you compare, TeO3 will have more oxidizing nature. Okay.
Right.
Hmm. Next, SO3, SeO3, and TeO3. This is the oxidizing property here. Now, bond dissociation energy of S double bond O is stronger. That's why this is a weaker oxidizing agent. Acidic strength wise, if you
Yes.
notice, as soon as you add water, you will get H2SO4, H2SeO4, and H6TO6. Problem with the tellurium is its double bond character is very weak. That's why telluric acid actually exhibits with 6 OH groups, because it
Yes.
can have the liberty to surround around 6 OH groups due to its size. So telluric
Yes.
acid will have all 6 hydrogens this way. So if I ask you
Yes.
basicity of telluric acid, answer is 6. It can give 6
Six.
hydrogens, but others can give only 2.
Two. Yes.
Okay. Next, if you notice, now next if you notice, uh, if you compare halides, oxygen, sulfur, selenium, tellurium, and polonium, you will see,
Oxygen, sulfur, tellurium.
yeah, with fluorine, only sulfur, selenium, and tellurium can form F6 cases. Okay, clear?
Yes, sir.
And when it comes to XeF4 here, it will be SF4, SCl4. This is with X4. And selenium can form with fluorine, chlorine, and bromine. Tellurium can form with chlorine, bromine, and iodine, not with fluorine. And same goes with
Right.
polonium as well. Okay,
Polonium.
1 second.
Right.
Check. EX2, you will notice it with oxygen, OF2, and OCl2. Okay. And SF2, SCl2.
Right.
Tellurium can make with chlorine and iodine. Polonium can make with chlorine and bromine. Honestly, this will
Yes,
not be
sir.
asked as which will make what. Okay. To be given as if the compound is given, you have to, assess its properties and so.
Yes, sir.
Oxygen with fluorine can give you O2F2. That is one thing which exists. Sulfur can make it with fluorine, chlorine, bromine, and selenium can make it with chlorine and bromine. Okay.
Bromine.
Now we expect the selenium to form something like SCX2, correct? But
Yeah.
unfortunately, selenium exhibiting +2 oxidation state is rare. This is called
Okay.
middle row anomaly. Okay.
Okay.
This inability to give +2 oxidation state is called middle row anomaly.
Mirror anomaly.
Okay. Right. These are the type of halides which can be formed here. Okay.
Yes, sir.
Now, only hexafluorides are known to us. That is, if you check SF6, it is inert and very heavy
Heavy.
gas. And SF6 does not undergo hydrolysis due to steric hindrance. Okay.
Okay.
And if you take TeF6, that undergoes hydrolysis to give H6TO6, which is telluric acid. Okay.
Right.
If you compare the rate of hydrolysis, definitely, because tellurium and fluorine bond is much weaker, that will give better hydrolysis than selenium and sulfur.
Right.
Okay.
Yes, sir.
Next is SF4 can readily undergo hydrolysis. That means SF4, when you hydrolyze, you will get this as sulfurous acid and HF.
Right.
And later on, you can see monohalides exist as dimers and undergo disproportionation. That is, if I take SeCl2, you can have 3 moles of Sc and SeCl4. So it will undergo disproportionation. All the monohalides, in fact, whether it is with selenium or sulfur, they will disproportionate in the same way. It will give you 0 and +4 oxidation state in all the cases. Okay.
Right.
Right. Next. Now, thereafter, if you notice, these are all the general properties, whatever we have discussed. Now, coming to specifically the dihydrogen compound here, you can see heating higher oxides. That means if you have lead O2 or MnO2 or Pb3O4, these are all relatively higher oxides. In fact, their lower oxides, lower oxides are more stable. Got it?
Bet.
Therefore, on heating it, you will notice that they convert into lower oxides and O2 gas is released. You know that we learned this in metallurgy that silver and mercury, they decompose very easily even at a low temperature. Okay.
So PB3O4.
Pb3O4 is the sindoor. Okay. It is a
No,
mix
that
of
I got.
PbO plus
It's
PbO2.
red or something, no?
Yeah, like this.
No, but like uh, how does red get oxidation state of?
Now see, basically it's a mixed oxide, but I have written it here. See, 2 moles of PbO plus PbO3, PbO2.
Okay.
And this mixture, when you heat it, this part, which is PbO2, that
That
will
also
convert into
becomes
PbO.
PBO.
Hmm.
ठीक Yes.
That's how it's gonna be. Right. Next, check out the heat. Next one is heating peroxides. If you notice BaO2 and H2O2,
Right.
BaO2 will make it BaO plus half O2, and this heating is called as Brin's process.
Right.
Peroxide, when you heat it, it will become H2O plus half O2, and it gets enhanced in the presence of MnO2. MnO2 is an catalyst. Got
Right.
it? Next, heating salts. Any higher oxygen containing salts, KMnO4, K2Cr2O7, KClO3, lead nitrate, and so on. In fact, all nitrates. Okay. See, KMnO4 will convert into K2MnO4. MnO2 is a black PPT, and then O2 gas will be released. K2Cr2O7
Right.
converts to Cr2O3, K2Cr4, and O2 will be released.
Right.
KClO3 becomes KCl plus O2, and lead nitrate will become PbO, NO2, and O2. These are all heating effects,
Right.
beta. This we have encountered already in salt analysis as a heating effect sheet. Okay. Hmm.
Right.
Nitrates also. Now, group 1 nitrates, they usually do not convert into oxides. They'll convert into nitrites, and rest part is released as O2. Okay.
Right.
And bleaching powder on heating will also convert into CaCl2, releases O2 gas. So there is, tons of reactions where we can easily get O2. Okay.
Right.
Next one is how we do the heating in concentrated sulfuric acid. Like KMnO4, when you react with concentrated H2SO4, it gets some kind of a dehydrated form. So you'll get Mn2O7, K2SO4, O2 is released, and SO2. Okay. In all these cases, it is acting like an oxidizing agent. Okay. Clear?
Right.
Hmm. So K2Cr2O7 is converting into that is still appearing to be CrO3, SO2, O2, and K2SO4. Okay. Here it
Yes,
is
sir.
the oxygen which is getting oxidized, sulfur is getting reduced. Same goes with
Oh,
PbO2, PbSO4, SO2, and O2.
bet.
And lastly, MnO2 will convert into Mn2O7. That is, here manganese itself is getting oxidized, sulfur is getting reduced along with oxygen
And
getting oxidized.
oxygen. Oxygen.
Now, as a part of large scale industry, you will simply make hydrolysis hydrolysis of water. That's the most economical way, so that we can get O2. Okay.
Right.
Next is, while getting electrolysis, we can also do liquefaction and distillation. Got it? So that
Right.
if you are distilling the air also, we can get O2, and then by distillation, I mean for liquefaction, we can get O2 in a liquid form, air in a liquid form. Then you do distillation
Right.
at different boiling points, you can get O2 gas.
Right.
Now see general properties of O2. O2 is a colorless and paramagnetic material. Okay. In fact,
Hmm.
you know that as per molecular orbital theory, it will have two unpaired electron in its anti-bonding orbitals. And
Right.
when you convert into liquid and solid form, O2 usually appears to be blue color. Okay. The
Hmm.
coloring is typically observed because when you have these two electrons in, pi star orbitals, correct?
Right. Hmm.
By absorbing heat, they'll keep interconverting them. That means when the light, sorry, by absorbing light, when the photons fall on it, the electron
Right.
in this pi star orbitals can take energy, take the energy, absorb the energy, and go to the higher orbit
Hmm.
and convert themselves into singlets. And from singlets, again, they can get back to the triplet form. So, this
Right.
conversion of singlet to triplet and triplet to singlet, this is happening via absorption of light. Okay. And the complementary color correspond to that is blue color.
Hmm.
Got it?
Yeah.
You know that why do we call it as triplet and why do we call it as singlet, correct? If you have two
Right.
unpaired electrons, it will be 2s plus 1. The total spin value is 2s plus 1. So 2 into 1 by 2 plus 2 plus 1. So which is 3. So this is called, you know, uh, spin multiplicity. So the spin multiplicity is 3, which means it is a triplet form.
Bet.
O2 reacts with most of the metals and non-metals, but it is inert towards certain metals, that is platinum, rhodium, gold, and iridium. Okay. And of
Hmm.
course, no reaction with noble gases directly.
Right.
And see, SO2 plus half O2, it gives a contact process combined form of oxygen converts into SO3. Hmm?
Right.
HCl plus O2 converts into Cl2 plus H2O, which is Deacon's process.
Right.
Okay. Next is, if you notice cumene plus O2, from this carbon you'll have OOH bond formation. Got it? And
Right.
this is a peroxy linkage which you have. And here, phenyl will start moving around to oxygen, bond will break onto this side, it will convert into a ketone, and phenol will form here. Okay. This is the
Right.
preparation of phenol. We have seen this is cumene peroxide process.
Yes.
And next,
Large scale preparation.
yeah, mostly these are the important reactions of O2. In fact, combustion reactions, they are all there. They are very generic
Hmm.
reactions. We're not going into that detail. Okay. Now, when it comes to ozone, what are the basic fundamentals we need to know? See, ozone cannot be prepared that easily. We need to take O2, make a silent arc discharge. Okay.
Okay.
So
What's up?
basically, you will have an electrodes on both ends, which are maintained at a very uh, high voltage, so that there is an
Okay.
arc produced in between. Got it?
That's new. Okay.
So in that presence of arc, the O2 molecule will break down into radicals, and few radicals will recombine with O2 to convert into O3.
O3. Hmm.
But the percentage formation of O3 is very less. Okay.
Right.
In fact, if you notice here, the delta S is negative because number of moles are decreasing. The heat is
Right.
required here to make it. That means delta H is positive. Okay.
Yes,
And you
sir.
can see this is negative, which makes this entire thing positive. Delta H is positive. So it is highly non-spontaneous reaction, isn't it?
Hmm.
So it cannot be prepared. Yeah, this being a non-spontaneous reaction, we will not be able to prepare the O3 that easily. Got it? You have to
Right.
continuously keep pushing the reaction towards forward direction. Then only O3 can form. But the backward reaction is highly spontaneous. That's why
Hmm.
If you leave O3 for a long time, it will again naturally it will come back to O2. Okay.
Right.
And when you have this percentage existing 90% and 10%, that I mean not just 90, I mean any amount of ozone present in that oxygen environment, it is called ozonide oxygen. Okay.
Right.
This is called ozonide oxygen. Now, pure O3 exists in three forms. One, in gaseous form, it is pale blue, liquid
Right.
form, dark blue, and solid form, it is violet black.
Right.
And O3, thermodynamically unstable with respect to O2 and easily decomposes. So,
What is the temperature for O3 to become solid?
O3 to become solid, I think minus 40 degrees or something. Okay.
Oh, okay, not too low.
Not too low. It is
Okay.
polar, na beta. Okay.
Hmm.
O3, when you heat it, it will become O2 plus nascent oxygen.
Hmm.
Now, nascent oxygen can be used as a oxidizing agent as well as a bleaching agent as well. Okay.
Yeah.
Now, of course, it is a very strong oxidizing agent. That's why all these reactions you can see they are all getting easily oxidized. PBS will get oxidized to PbSO4. H2S will get oxidized to colloidal sulfur. NO minus 2 will convert into NO3 minus.
Hmm.
Arsenate will become arsenic. Okay. So
Right.
ASO4 3 minus. And with HCl, Cl2, I mean, chlorine will get oxidized. Fe plus 2 will get
Hmm.
oxidized to Fe plus 3. SO3 2 minus will convert into SO4 2 minus. So these are all
Hmm.
easy oxidizing reactions. In fact, when you react with KMNO4, the oxygen present in it will also get oxidized.
Hmm.
Okay. So K2MnO4, if you have, that means it is plus 6, and that will get oxidized to plus 7 in the case of manganese. Okay.
Hmm.
And O3 can oxidize I minus also. If it is in a neutral medium, it will convert into I2. If it is in a basic medium, that I2 will further convert into IO3 minus and IO4 minus.
Right.
Okay. And see this, if at all I keep that in a neutral medium like water, okay, first, like I said, I2 will form and I2 will further have a formation of HiO3. Okay, correct.
Hmm.
But if it is in a basic medium only, IO4 is observed. Otherwise, you will end up only as HiO3. Okay. And
Okay.
if I2 is dry, there is no water in it, then it is like this. It is forming IO3 minus, correct? Large
Yeah.
amount of IO3 minus will be formed, and some part of iodine will exhibit as iodine plus 3 oxidation state.
Right.
So you can see 1 mole of iodine plus 3 and the other moles were IO3 minus of 3 moles. These two combined form is
Right.
called as I4O9.
Right.
So it is a solid form which you will observe as I4O9. Okay.
Right. Yeah. Sorry.
Next is check out what is the reaction with KOH. See, KOH plus 5 moles of O3. Okay. Now this is again an anhydrous form. Got it? So that
Yes.
KOH will
Yes.
convert into KO3 minus. KO3 minus is
KO3
what beta? It
minus
is like O3 minus with K plus. This is called an ozonide. O3
ozonoid.
minus is called an ozonide where oxidation state is minus 1 by 3.
Nice. Okay.
And it will give you an orange red PPT of KO3. Okay.
Okay.
In fact, this is used for confirmation of ozone. Correct? Presence of ozone. Yeah.
Oh, in liquid form.
No, no. Ozone could be in either solid or sorry, liquid or gas form. But the
अच्छा
confirmation is that it will give an orange red PPT with
orange red
KOH.
PPT. ठीक है.
And you see, all group 1 elements except lithium and sodium, they all will form these ozonides. And of course, as the size increases, the ozonide form stability increases, which is same as
So
the
you can use
superoxides also.
rubidium hydroxide or cesium
Yeah.
hydroxide
So
also.
like we have KO2, RbO2, these are all superoxides. Even for
Right.
superoxides, the stability goes this way only, right? So
Right.
as the oxygen number increases, the size will always help it to make it more stable.
Right.
Done, beta. Okay. Right. Okay. So we'll do